Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science lesson videos, and we're going to be looking today at radioactivity for GCSE science and physics. In particular, what we're going to look at is the properties of radiation. So by the end of today, the objective, the one major objective for today, is to be able to state, describe and compare the three main types of radiation. What are they? What are they made of? How do they work? That is what we're going to aim to establish today. And there will be activities as we go along for you to do just that. Now, today's lesson is not going to focus on radioactive decay. Now, radioactive decay is something that most of you hopefully would think would be associated with this, and it is. But that's a lot more mathematical and gets into the intricacies of nuclear physics. We're not going to do that today. We're going to look at the radiation that comes out of radioactive decay. But if you want me to do a lesson on the mathematics and nuclear decay and atomic notation, all of that stuff, I'm absolutely down to do that. Let me know via the comments. So, we've got plenty to dive into. I won't spend too long in this introduction. If you have any questions and you're watching this live, please do let me know in the Premiere chat and I will answer as best I can. Otherwise, if you're watching this post-hand, you have the comments to make sure you can ask questions and make requests, because that is what I enjoy about this series, is listening to you guys and putting out episodes that you will watch and enjoy. So without further ado, let's begin. So to get us started for today, I wanted to ask a very simple question. Well, simple in concept, but maybe not so easy to answer. What is the difference between an atom and an ion? So atoms and ions are two terms you've probably met before. Certainly you'll have met atoms before, and if this is not your first radioactive rodeo or atomic rodeo, you'll have definitely also come across ions because of what ions are. But do you know the difference? Is there a difference? So that's the question I would like you to answer. Now we're going to come back to ions later in the video and what they are and how that feeds into radioactivity. So as with my recent videos, I'm not going to provide the solutions here. They will be linked in the description of this video. So go down to the description and the top link will say starter solutions, or solutions to the starter is I think how I phrase it. So check there, that will give you the answer to this question. You can watch that video when you're ready and come back to this one. So give yourself a minute or so to have a think, write something down, check the solutions video if you need to, and then we'll move on and we'll introduce the types of radiation. All right, let's get ourselves into some radiation, shall we? Not literally, because that would be dangerous. Mostly. So, there are three main types of radiation that we are going to explore throughout this video. There is a fourth, and we will mention it here, but we're not going to explore it in the same depth as the others. So, the three main types of radiation that you need to know and would be expected to talk about even in 6-mark questions sometimes are alpha, beta, or beta if you're so inclined to say it that way, and gamma. Now, the fourth type is not delta, sadly, but these are the three main types of radiation that you're going to encounter. But that's just some Greek letters. What are these things? What are they made of? How do they work? Well, we're going to make that in full throughout the video, but in short, I'm going to give you now the very basics of what these things are made of and where they come from. So, first, alpha. This is an alpha particle, sort of. It's not really a particle, it's a molecule of different, well, in truth, it's a nucleus. So what this is 2 protons and 2 neutrons stuck together, not quite as rigidly as this because atoms are not stuck together with blue tack, to form a particle, a helium nucleus, if you will. Because you've got 2 protons and 2 neutrons, it's basically the same as helium-4, which if you look at the periodic table, has an atomic number of 2, mass number of 4. That is helium-4, and that is what an alpha particle is made of. Now, if an alpha particle is 2p and 2n, which is how we sort of note it in this sense, we're not going to write it in full atomic notation today. Where does it come from? Well, when an atom gets very, very heavy, it struggles to hold itself together because the forces between the protons and neutrons is not strong enough to hold them together. So when you have very heavy nuclei, they are unstable. And what that means is that at some point, at random, they will fall apart. And when they fall apart, they sometimes release, actually very often they release, these alpha particles as a way to lose mass and therefore get more stable on the sort of energy scale, which is something you meet up at A-level physics. Now, beta radiation is a little bit different. So beta radiation is actually even simpler than the alpha particle, which you may not even think is that simple to begin with. A beta particle, or as I say, beta, depending on where you are in the world, is one of these. No, it's not a pink bouncy ball. That's an electron, if you look back to my starter solutions for this video. So this is an electron. Now, you might be thinking, oh, well, that's very easy then. If it's an electron, it must come from the electron shells that are all around the atom, which you've probably met before. But it's actually a bit more complicated than that. So, neutrons are actually slightly unstable. You can see because it wants to roll away. Neutrons can decay, and sometimes it is better for an atom or for a nucleus to decay its neutrons, or for an atom's neutrons to decay in order for it to become more stable. Now, when it does that, what it decays into, can't do the magic trick, is a proton. So the neutron that we had is now a proton. But neutrons have no charge and protons do. So in order to gain that positive charge, what the neutron does essentially is it decays, transforming itself into a proton and releasing an electron along the way. So an electron comes out from the nucleus and is ejected as beta radiation, and you're left with a proton. So I'm going to put that sort of in brackets, electron from the nucleus. It is not an electron from the shells, which is a common misconception. So make sure you have that in your notes somewhere. If you want to watch that back and write it down, then you are more than welcome to. So it comes from stabilizing atoms that have got essentially too many neutrons. If an atom or a nucleus has too many neutrons, it will eject beta radiation. Now, gamma radiation is actually not a particle at all, not in the sense like alpha, but it is actually an electromagnetic wave. Now, you may or may not have met the electromagnetic spectrum yet. I think certainly it's a GCSE topic, and it's certainly taught in some place at Key Stage 3. So you might have heard of the electromagnetic spectrum, and the gamma is the highest frequency and highest energy portion. It's up at the right-hand side of the electromagnetic spectrum quite often. It's got a lot of energy. And where these come from is sort of, well, the official term that you'd use at high-level degree physics is like de-excitation. Basically, when an alpha or a beta decay happens, the atom is not always, or the nucleus is not always in its most stable configuration. So it might have, just to use this, two protons like this. And protons don't like being like this because they're positive and they repel each other. So what happens is the nucleus does a quick little shufty round and rearranges itself so that the protons are now apart. But that takes energy, and that energy is released in the form of gamma radiation. So the best word I can use really is reconfiguring the nucleus, which is a big word and probably not the most scientific term you could use, but it's a case of getting the nucleus into a more stable configuration, a more stable sort of layout of protons and neutrons when the decay has happened. It's sort of a leftover product of the decay quite often, not always, but quite often. Now, the fourth type of radiation, which we're not going to explore in much detail today, is actually the neutron. You can have radioactive decays where all that is released, I've dropped the other one, is the neutron. Nothing else. That's all that gets released. Now, this can happen, but it's a lot rarer than, for example, alpha, beta, and gamma. So we don't know as much about it, or you certainly don't need to know as much about it. We probably know plenty about it. I've just forgotten half the research. So yes, neutron, I know capital N should be a lowercase. That is the fourth type of radiation, but you don't see it very often. You just need to be able to do the maths with it, which we're not going to do today. That is an entirely different lesson, as I mentioned in the introduction. So, with those types of radiation, and I've rambled on for a long time about them, can you now take down any notes you want to? We're going to dive into detail, and we're going to start with the alpha particle. Before we get into the full details of the types of radiation, which we are going to do in a moment, I promise, just panning across the screen right now, and then it will come up in full screen in a moment, is a table that I have designed that contains all of the core properties of radiation that you will need to know and that we're going to address throughout the lesson. Now, this is not a comprehensive, absolutely everything there is to know about radiation table. There are more things that you could add to it. For example, applications of radiation, which is an entirely separate lesson as part of the radioactivity topic. And we don't get into the atomic notation and the mathematics behind them because that's involved in the nuclear decay lesson that I'm hoping to do maybe in the not too distant future. So if you are someone who is working through this lesson and treating it as an actual exercise, can you either screen cap, copy paste, draw out, whatever, the table that is on the screen at the moment, so that you can fill it in as we go through the three types of radiation in detail, and then you can use it as a reference point for your revision and for the quiz that we're going to have at the end of the lesson. So pause the video now, copy the table down if you are doing so, and when you're ready, let's get into the various types of radiation. So the first type of radiation we're going to explore in depth today is alpha radiation. So we already established that an alpha particle is made up of 2 protons and 2 neutrons. We established that earlier on. So that's what it's made of. But we can then, from that information, infer a couple of properties based on the table that you saw and had explained to you a few moments ago. So you can be filling that in as you go along if you've already copied it down as I requested. So the first question we can ask is, what is the charge of an alpha particle? What do you think? Have a think to yourself. You need to pause the video, do so. What is the charge of an alpha particle going to be? Well, let's take a look at the components. So, we know that protons have a charge of +1. They're positively charged. We talked about that in the starter solutions. Neutrons have no charge because they are neutral, hence the name. And electrons have a charge, relatively, of -1. Now let's put our alpha particle together. Proton, neutron, proton again, and neutron again. So we have 0 + 1, 0 + 1. Add that up together, we get a charge in total of +2. The charge of our alpha particle is +2. The second question we might ask is, what is the atomic mass? We could ask about the atomic number as well, but normally we would talk about the atomic mass because of what it means for some other properties. So the second thing we need to remember is, how do we calculate atomic mass? Well, each proton has an atomic mass of 1, relatively. Each neutron has an atomic mass of 1. And an electron has a mass of 1/1620, but effectively we call it 0. It is so small as we don't need to count it for measuring the mass of the atom. They are negligible. So let's see what we've got. Well, we already did it. 2 protons, 2 neutrons. What does that leave us? 1, 2, 3, 4 things with a mass of 1 each. Therefore, the atomic mass is 4. Now, the next one on your table is the ionizing power. So we talked in the starter solutions about ions, and we mentioned them at the starter as well. Ions essentially are charged atoms, and they come about quite often when electrons get added to or taken away from the shells of the atom, from the shells that are orbiting the nucleus where you find your electrons. Now, radiation, you may be surprised to know, is very, very good at ripping off and knocking off electrons. It's very good at it. So if you've got a shell full of electrons just sitting there, all happy as Larry, and there's the nucleus, and along comes some radiation, even if it doesn't hit it, it might come in and knock off an electron like that, but that's quite rare. More often it will come by and the electrons will just be ripped away. They'll be ripped away along with the radiation. And that leaves an ion behind. Now, how effective a piece of radiation is at causing ionization, which is that term of creating an ion, is ionization. So I'll clear this off this side and write that as a key term, which you will get, which you've had the definition of, but I won't rewrite it, of ionization. How good is something at creating an ion by ripping off electrons particularly? Well, an alpha particle has a charge of +2. So its ionizing power is actually quite high because it has a large charge. Not necessarily plus minus, but the number on its charge is very, very high compared to the other one. So its ionizing power is high. However, this comes at a cost. Well, actually, the ionizing power doesn't really come at a cost, but something else does come at a cost, and that's the range. So radiation does not travel forever. If it did, then the fallout from certain nuclear incidents would probably have been a lot worse. But radiation can be stopped and eventually will run out of distance before it either slows down or is stopped altogether. Now, in air, alpha particles don't get very far. In fact, as part of this topic, you do about applications of radiation, and alpha particles are used in your smoke alarm, and it's perfectly safe because they can only travel a few centimeters in air. So if I had some alpha particles and I was launching them from over here, and I had a detector over here to see how many alpha particles hit it, probably pretty much none of them. They wouldn't get there because this board's reasonably long, it's nearly a foot long, and they would barely get there because they don't have a large range in air. And as for what can stop them dead, because air doesn't stop alpha radiation dead, it can slow it down and it will only get so far, but some of them can stop it dead. And for alpha radiation, there are sort of two examples you should keep in mind. The first is a sheet of paper. Yeah, that paper you're probably writing on, yeah, that could stop some alpha radiation. And the other is your skin. That's important later when it comes to medical physics. But basically, alpha radiation outside your body cannot get through your skin. It can hit your skin, but your skin will stop it dead, which is really, really useful, in fact. So that is everything you need to know about alpha radiation. Take the time to fill in your table if you've not been doing so already, and then let's move on to beta radiation. So a beta particle. Beta radiation is just an electron, as you might remember. Now, let's go through the same process as we did with our alpha particle. What's the charge of a beta particle? What's the charge of an electron? -1. I talked about it literally 4 minutes ago. -1. What is the atomic mass of a beta particle? What's the atomic mass of an electron, relatively speaking? Well, it's 0. Now, officially, if we're being pedantic, we could say it's 1/1620 or something, but no, we're not. If we're being pedantic, we are, but relatively speaking, a beta particle has an atomic mass of 0. So, what does this mean then for its ionizing power? Well, a beta particle is reasonably ionizing, but the amount of power radiation has to ionize is based on its charge. Remember, not the plus or minus, it is based on the number. So 1 is less than 2, so we say that it has less than alpha. Less than alpha. The sort of term I would normally write is probably medium. A beta particle is quite good at causing ionization. It's not brilliant, and certainly you get better results out of an alpha particle, but it can do it because it has got some charge to it. What about its range in air? So this comes back to the mass. The heavier a piece of radiation is, the less distance it's going to get, normally because it's bigger as well. And beta particles are much smaller than alpha particles, and they also are much, much lighter. However, this zero flatters to deceive, which is why I talked about that 1 over 1,620 a minute ago. So beta particles can get quite a long way through air before they eventually get stopped. In fact, they can make it several meters. So probably across the room is probably not a bad place to start, depending on what room you're in, of course. But a beta particle could certainly make it across most rooms. It might even get across some bigger rooms, depending on how fast you fired it. It's got a decent range on it. Not infinite, but a decent range before it gets stopped by air. But that doesn't mean it's unstoppable. So if we're stopping a beta particle, what we typically use is something a bit thicker than paper or skin, because it takes more effort to stop it. You need something a bit thicker to absorb it, and you need something that has got a slightly better capacity to do that. So what we use quite often to stop is aluminium. Yes, I know if there are Americans watching, you'll be saying aluminum at me right now. No, aluminium. Sorry, it's aluminium. At least it is for us over in the UK and the rest of Europe. So aluminium stops beta particles. And this is actually used as another application. When you're doing something called thickness monitoring, which you would learn about as part of this topic, you can change the thickness of an aluminium sheet using electric computer signals from a beta radiation source. The thicker the aluminium, in fact, I'm going to write this in green because I've got a little bit of space. So thicker aluminium is better at stopping beta, and you can use this to monitor how thick aluminium sheets are, which is very useful, for example, in manufacturing. They actually do use this method, which is something you'll learn about as part of this topic, though probably not with me. So that's beta radiation. Now we've got one more to do, the gamma ray. So gamma radiation is a little bit different to alpha and beta, as we talked about earlier. The first big difference is it's not a particle. It's an electromagnetic wave or a ray. So sometimes you hear of gamma rays. So it's an electromagnetic wave on the EM spectrum. I'm just going to write a little comment here that it is a high energy one. So you might not have met properties of waves yet, and you certainly might not have met all the bits to do with it, but gamma rays have very, very high energy, which is what makes them so dangerous. So what do you think is going to be the charge of a gamma ray? It's a little bit difficult because we don't have any protons, we don't have any electrons, so we can intuit an answer. But, well, do electromagnetic waves have charge? And the answer, in truth, is no, they don't. The charge of all EM radiation is 0. Otherwise, all light would be very, very dangerous if it was charged. It would be like being bombed with electrons that can also move through anything. It's quite dangerous. So, no, they have no charge. What about mass? Well, again, do we have any protons, neutrons, or electrons? No, we don't. And whilst it's something you wouldn't really be able to prove until you got up to something like degree level, or certainly A level, light and all EM radiation has 0 mass whatsoever. I'm actually going to write in green, actually 0. Not this 1 over 1,600 that we ignore nonsense with the electron. No, actual 0. EM radiation and light has no mass. The reason for that is because it travels at the speed of light. It's basically down to Einstein's E equals mc squared plus all that stuff. Yeah, not getting into that. Would love to, but I'm not going to. So the next question then is the ionizing power of gamma radiation. You should hopefully be able to intuit an answer based on what we've said about alpha and beta. And the answer is actually that the ionizing power is quite low, because gamma rays have no charge. Yeah, sure, they've got a bunch of energy, but they have no charge whatsoever. So their ability to rip and knock off electrons is actually quite reduced. It's very difficult for them compared to alpha and beta. But, and this is the big caveat, stopping gamma radiation is a nightmare. It's an actual nightmare. Because, remember I said that it was based on mass. The bigger something was, the heavier something was, the easier it was to stop. Yeah, how do you stop something that has no mass whatsoever and is essentially just a light ray? How do you stop that? The answer is with great difficulty. With great difficulty. And in air, it's practically infinite. So I've written this symbol here. This means sort of a wiggly equal sign. It means approximately. Or roughly. And this symbol here, in case you've never met it, is infinity. So that means that roughly, a gamma ray, if fired in air, will go on forever and ever and ever and ever and ever and ever and ever. It will pretty much never be stopped. It's very dangerous as a result because it can get through a lot of things. So how do you stop it? Well, we've seen that particularly with radiographers, you've got those lead aprons for X-rays, but you're going to need a bit more than that to stop a gamma ray dead. So what you actually need, some good old-fashioned concrete. So this is why nuclear reactors, which is something you would do as part of this topic, are usually contained in big metallic cages that also have got big concrete bunkers almost built around them, these concrete shells, in order to absorb the gamma radiation, to stop any radiation leaks from the reactor should there be an issue. That's why they've got this concrete around them, which you will meet later, is to stop gamma radiation. So that's gamma. In fact, that's all the main types of radiation, everything you need to know about them. This is your chance now to complete the table and finish it off so that you've got that ready for your notes. And we'll have one last task, a couple of quick questions to allow you to compare and explain the differences between the types of radiation. So now we're going to have a few quick quiz questions just to finish off the lesson. So I'm going to fire these off rapid fire at you. You're going to have a minute to answer them on your own, and then you're going to do the answers here. Now, I'm not going to put them as a separate solutions video because we're going to go through these rapid fire. They're going to be quick, short clips, and then you'll get the answer. So, first question. Which type of radiation is blocked by a sheet of paper? Is it A, alpha radiation, B, beta radiation, or C, gamma radiation? If you get the answer, your challenge is why. Why is that the answer? So give yourselves no more than a minute, pause the video, pick your answer, justify your answer, and then come back. So, the answer is alpha radiation. Alpha radiation is blocked by a sheet of paper. As for why, well, that comes down to its mass. So because the alpha particle, actually it's not because it has the highest mass, it's because it just has a high mass. Because it has a large or a high atomic mass, it is very easy to stop. Remember, it has that low range in air. Because it's so big and so heavy, plus large size, second reason. So a high mass and a large size means that it is easily stopped and can be stopped by a sheet of paper. Now, question 2. Question 2. Which radiation type is not stopped by aluminium? And if you work out the answer, why? Give yourselves a minute. Off you go. All right, hopefully you paused the video and got yourselves an answer. The answer is gamma radiation. Now, there may be a few of you who might have said alpha because you've got in your heads oh, beta is stopped by aluminium, so alpha isn't? Well, you might be tempted to think that, but bear in mind that alpha is stopped by my sheet of paper right here. This little sheet of paper could stop some alpha radiation from getting through it. So I think if I was to replace that with some aluminium, which is what, for example, your drinks cans are made out of, they would do just fine at stopping that alpha radiation. We already established that beta radiation is stopped by it, so the answer must be gamma. But if you put alpha, I'd understand why. The reason why? They have no mass. It's very, very light. And that means that gamma radiation can get a long way because it is very, very light. You may also want to talk about the fact that it's got a high energy. You could also talk about that as an option. The main thing is the mass, but because it's got so much energy, it's very good at, and I used this term once, at penetrating through materials and surfaces. It's very good at that, and so it is able to get through a lot more things. Right, question 3. Question 3. Which type of radiation has a negative charge? There is no challenge question here, so you can ignore this. Which radiation has a negative charge? Well, actually, there is a challenge for it as to why, so yeah, I'll leave that in. So, answer. Beta radiation has a negative charge. Why? It's an electron. And electrons have negative charge. Nice and straightforward, that one. Hopefully it didn't require too much explanation. Alpha, you might remember, +2. Beta, -1. Gamma, 0. Okay, question 4. Question 4. This one's going to take a little bit longer and might require a bit more deductive reasoning. Which type of radiation is most dangerous to us when it is outside the body? Which type is most dangerous to us outside the body? Take your time, 2 minutes, work it through. So, the answer that you would typically be expected to give is gamma. Now, if you've said beta, I can understand why. Alpha I'll dispel in a moment, but let's address the reasons why gamma is the correct answer, because there's 2. Well, actually, it's pretty much down to 1. Well, it's 2. The first is its long range. Gamma radiation can travel a long, long way. And the second, the fact that we say it is very penetrating. It is good at getting through things and stuff. So gamma radiation, if it's outside your body, could easily pass through your skin and get at the cells underneath. It could even pass through your watch, your jacket, and your skin into your bones, and maybe even out the other side quite easily. It's that good at getting through stuff, and it's got a long range. Then this second reason is why beta radiation is not usually the answer. Now, if you had a beta source right here, that's really bad because it can get through your skin, but it won't get through everything in your body because it's not as good as gamma radiation and it doesn't travel as far, but it can get through, and that makes it dangerous because it's more ionizing than gamma. But because it's only got a range of a few meters, we typically say that gamma is the most dangerous in general. Now, as for alpha radiation is actually the right answer to a very different but similar question. If you were inside the body, so if you swallowed 3 sources of radiation for whatever reason, the alpha source is the most dangerous to you. Now, there's 2 reasons for that. The first is its ionizing power, and the second is it can't get out. Remember what I said about alpha radiation? It can't get through your skin. So if an alpha particle, or say a pile of them, are sat in your hand, like as in literally inside your hand, then they can't get through your skin and get out again, which means they're just going to sit there and keep on ionizing for ages. And they're very, very good at ionizing, which makes them a huge danger when they're inside the body. But if they're outside the body, apart from to your skin, because they can hit that, they can't affect you. They can't get through your clothes, they can't get through your skin, they can't get through anything. But once they get in, they're very, very dangerous. Outside, usually it's gamma. Inside, typically it's alpha. Right, that is going to be the final question, because that was a bit more longer thinking and a bit more challenge for you and a bit more explanation. So that brings us to the end of today's lesson, all about the types and properties of radiation. I expect to follow this up, maybe not next week, but soon, with a lesson on radioactive decay, the mathematics behind all of this stuff. So what does alpha decay look like, and what does it do to a nucleus? What happens in beta decay, and what do we get left over? We'll look at atomic notation, and we can look at decay chains as well. But today, remember the objective I gave you at the start. We should be able to state the main types of radiation, describe them, and compare them. Well, let's think about it. Can you name the 3 types of radiation? Yes, you probably can. Can you describe them? Why, yes, you have this table right here that you will have filled in. Now, ignore that column. That column's atomic notation, so you won't have done that today. But there you go. You fill that table in. You can describe them. Can you compare them? Well, you've just said to me which one is the most dangerous outside and inside the body, so you've been able to compare them. You've been able to say which ones are stopped by what. You've talked about their charges. Yeah, I'd say you'd be able to compare them a bit. And you can obviously do a lot of practice questions and past paper questions, and there's some longer answer questions about this stuff as well, if you are so inclined. So that is all for today's video. Thank you very much for watching, and I do hope you have enjoyed it. Let me know your thoughts in the comment section down below, and if you have any requests for future videos, I'm always willing to hear them and try and do them if I can. So that is all. Thank you very much for watching Tactica Imperialis, and this has been the properties of radiation. I'll see you all again. Goodbye.